Sure. Okay, thanks, Natalia, and thanks, John, for organizing this and inviting me to speak here today. It's a real pleasure to be able to speak here today. So the purpose of this talk is really twofold. Firstly, to give an idea of some of the tools and techniques that we use when studying self-affine carpets, and secondly, to say something about the less familiar notions of fractal dimension, like Assouad type and intermediate dimensions. And I'll mention lots of people's work, but of my own work, I'll mention a project that I've done with István Kolozsvári, and also I'll briefly mention a project that's in progress with Jonathan Fraser and István as well. So let me very briefly recall some things which will be familiar to everyone, I'm sure. An iterated function system is a finite set of contractions from some closed set to itself. And in our case, we can take the closed set to be the closed unit square. Hutchinson's theorem says that there's a unique non-empty compact attractor that's equal to the union of its images. And in the case of self-similar sets where the contractions are similarities, if we iterate the IFS, we can see that the cylinder sets look roughly like balls or squares. Whereas if we take an IFS of affine maps, then the cylinders look more and more elongated at small scales. And these can line up in a way that can cause more interesting dimension properties than for self-similar sets. So in order to obtain dimension results, we'll assume the strong open set condition throughout the talk, which means that there's a non-empty bounded open set V which intersects the attractor, and usually we can take V to be the open unit square, such that V is mapped into itself under the contractions with the union disjoint. And as we all know, then for self-similar sets, if this is the case, then they will be Alfors regular, and all the notions of dimension, like Hausdorff box and Assouad dimensions, will coincide and satisfy Hutchinson's formula. So the sum of the contraction ratios raised to the power of the dimension equals 1. And I'll say a bit more about the different notions of dimension later on, but these are generally ordered in the sense that Hausdorff dimension is less than or equal to box dimension, which is less than or equal to Assouad dimension, and they give different properties about the set. In terms of self-affine sets, it's broadly divided into two classes of results, the generic theory and the exceptional theory. So the generic theory says that in many situations, Hausdorff and box dimension will coincide with Falconer's affinity dimension formula. So for example, by work of Falconer and Solomiak, if we fix the contraction, the linear parts of the contraction, and randomize the translates, then often the dimensions will satisfy this formula. Or in a different direction, Barani, Hochman, and Rappaport have shown that if the matrices satisfy mild non-compactness and irreducibility assumptions, then the box and Hausdorff dimensions will again be given by this formula. But this talk will be all about the exceptional theory, where for carpet-like sets, the two coordinate axes can be preserved, so they're not irreducible, and the cylinders can line up at small scales, which can result in different notions of dimension, taking different values, as we'll see. So let's start with the simple setting of Bedford-McMullen carpets, and here we divide a square into an m by n grid with m being less than n. So here m is 2 and n is 3, and if we iterate the IFS, we'll end up with a carpet like this. And to state the dimension results, we need to introduce some notation. So let gamma be the eccentricity of the maps, log n over log m. Capital M is the number of non-empty columns. N sub I is the number of maps in the ith non-empty column. So n1 is 2 and n2 is 1 here. And capital N is the total number of maps. So 3 in this case. And the IFS is just the set of contractions that send the unit square onto each of these rectangles that we've chosen. So these were introduced independently by Bedford and McMullen in 1984, who also calculated their Hausdorff and box dimensions and showed that generally they're different. This is the formula for the Hausdorff dimension. This was calculated in slightly different ways by Bedford and McMullen. Bedford used Eggleston-type estimates on the Hausdorff dimension of sets whose digit expansions have whose digits have certain frequencies in their decimal expansions, whereas McMullen put an appropriate measure on the carpet, now known as the McMullen measure, and applied the strong law of large numbers in a clever way to prove this result for the Hausdorff dimension. And if you haven't read McMullen's very first paper, I'd recommend that you do, because it's a really nice, simple argument in fractal geometry. One thing that we very often have to do when we're working with self-affine sets is to divide the carpet into approximate squares. So if delta is a very small number, then let k be such that delta is approximately n to the minus k. So k is the integer satisfying this. And when I say approximately equal to, I'll always mean up to multiplicative constants, which depend only on the carpet, because this will not affect any dimension results. So an approximate square of size delta can be represented by this string. So what's going on here is that if we iterate the maps k times, then we'll end up with a cylinder set which looks like a rectangle whose height is approximately delta up to constants and whose length is approximately delta to the power of 1 over gamma. And this is why gamma keeps coming up in the dimension formulae. And if we then choose columns inside this cylinder, we will gamma k minus k times will get approximate squares, which look like a square up to distortion by some absolute constants. Now, to calculate the box dimension, we just need to count up how many delta approximate squares there are in the carpet. And there are k choices for the first part of the symbolic representation and gamma k minus k choices where we're choosing the columns. So this quantity can then be shown to be equal to delta to the power of minus this quantity after some algebraic manipulation, and therefore this is the box dimension. So that talks about the global scaling behavior of the carpet. How about the local scaling behavior? Well, this is captured by the Assouad type dimensions. So these describe the extremal local scaling behavior of the thickest parts of the set at all pairs of scales. So in particular, the Assouad dimension is the infimum of exponents alpha, such that there exists a positive number c, such that for all points x in the carpet or the set, and all pairs of scales, little r and capital R, the covering number of the part of the carpet which lies inside the ball of radius capital R and center x, with respect to the smaller scale, little r, is bounded above by the constant times the ratio of the scales raised to the power of alpha. So because we're working over all parts of the carpet, this is the largest notion of dimension that can reasonably be defined using covers. And if we want to fix the relationship between the two scales, say little r is the larger scale to the power of 1 over theta, then this defines the Assouad spectrum, which was introduced by Fraser and Yu. And this is a family of dimensions depending on the parameter theta, which lie between box and Assouad dimension. It's always continuous in theta, but it's not necessarily monotonic. As theta goes to 0, you approach the box dimension, and as theta approaches 1, you reach the quasi-Assouad dimension. And this more broadly falls into the category of dimension interpolation, where we want to take two different notions of dimension and find a family of dimensions which lie between them in a geometrically meaningful way. So to calculate these dimensions of self-affine carpets, it suffices to consider approximate squares such that all of the columns in its representation come from the column with the most number of maps in it. Let's call that n max. And then if we look at such a square up to resolution r to the power of gamma, it will look like a product of self-similar sets. So on the horizontal direction, it will look like the projection of our carpet onto the x-axis, and the product of this, it will look like the product of this with a self-similar set that's generated by n max contractions, each of which has ratio 1 over n. And when I say looks like this up to a certain resolution, what this means more formally is that this product set will be a weak tangent to our carpet with a particular rate of convergence. So in other words, the Hausdorff distance of the blow up of that part of our carpet to the product of self-similar sets will tend to 0 with a certain rate. And then we can use the fact that the Assouad type dimensions are known to be related to weak tangents by results of Mackay and Tyson for the Assouad dimension, and Garcia and Hare, for example, for the Assouad spectrum, to show that the Assouad dimension of the carpet is the dimension of this product of self-similar sets, which is just the sum of the dimensions of the individual self-similar sets, which is given by this formula. And also the Assouad spectrum is the same thing, provided theta is sufficiently large, so theta is greater than 1 over gamma. The Assouad dimension result was proved by Mackay, and the Assouad spectrum result was proved by Fraser and Yu. And this can also be proved directly without appealing to weak tangents. When theta is smaller, then a cylinder set of height r to the power of 1 over theta inside the approximate square has length much less than r. So we don't have this product structure. And in this case, to calculate the Assouad spectrum, we suppose that capital K is such that the larger scale is n to the minus k, and little k is such that the smaller scale is n to the minus k. And then we need to count up how many smaller approximate squares there are inside the larger one. So if we fix a larger approximate square with a certain symbolic representation, then for the smaller square to lie inside it, the first part of the symbolic representation has to be equal. The second part has to lie within, consist of maps in the same column as the maps of the first part. Then we can have complete freedom with choosing the maps in the third part. And then in the last part, we're choosing columns, and these can come from any column. Counting this up, we see that the number of smaller squares inside the larger square is bounded above by the situation where the larger square is only choosing maps from the column of maximal dimension. So we have gamma k minus k positions where we choose where we have n max, that's for this part, and then we have this many positions where we can choose capital N maps, and then this many positions where we can choose capital M columns. And then after some algebraic manipulation, this comes to being r to the power of 1 minus 1 over theta times this quantity over here, which is the Assouad spectrum of the carpet. So if we plot the Assouad spectrum as a graph against theta, it increases in this convex way until a phase transition at 1 over gamma, and then we see that it's equal to the Assouad dimension from then on. And we can observe from the formulae that the dimensions that we've considered will coincide if and only if the carpet has uniform vertical fibers, so the same number of maps in each non-empty column. In this case, the carpet is R-force regular, but otherwise all the dimensions will take different values. So for the carpet on the right, for example, all dimensions will take different values. And now, with Jonathan Fraser and Istvan Koloshvadi, I was considering what can be said about the Assouad spectrum of more general carpets, in particular carpets of Lalley-Gatzouras type. So these were introduced by Lalley and Gatzouras, who calculated their Hausdorff and box dimensions. And here we take some columns in our approximates. We take a square and we divide it into some columns, which can have different widths in this case. And we choose some maps within each column, which all satisfy the important condition that they contract more in the vertical direction than in the horizontal direction. And this is important so that cylinder sets will always be longer than they are high. It's really important that we have this column structure, because this tells us that the self-similar set that you get when you project the carpet onto the x-axis satisfies the open set condition. And if you didn't have this, you could imagine a situation where the projection was some self-similar set with super exponential concentration of cylinders and no exact overlaps whose dimension we don't even know. And in that case, it would be impossible to compute an exact formula for the dimension of the carpet, because that would be a harder problem than the exact overlaps conjecture, and you would have to try and get a formula in terms of the dimension of the projection, for example. But in this case, we don't have to worry about that, because the dimension of the projection has the projection is well separated. And let me also just mention that the three-dimensional versions of these Lalley-Gatzouras type fractals are surprisingly what's used in the famous dimension drop paper of Duss and Simmons as an example of an expanding repeller whose Hausdorff dimension is not realized as the Hausdorff dimension of any invariant ergodic measure. But I haven't looked at the proof of that, so I don't know. I don't have a good intuition for why it satisfies that somewhat surprising property. In terms of the Assouad type dimensions of these carpets, we'll assume for simplicity for the moment that there's only one type of map in each column. In other words, the eccentricity of the map depends only on the column. And let theta sub I denote this eccentricity, log AI divided by log BI. So in this case, theta 1 is less than theta 2 is less than theta 3. And it suffices to consider cylinders to work within cylinders of height capital R, which are formed only using maps in the first column, the most eccentric column. And this is because this will give us a maximum number of entries in the second part of the symbolic representation when we're dividing the cylinder into an approximate square, which will mean that it will look thicker at smaller scales. Excuse me if we do. Sorry about that. So in terms of the Assouad dimension, which was computed by Mackay, if theta is large enough, our carpet will again look like a product of the projection with the appropriate the part of the carpet which lies in a square formed using the column with the maximal dimension of the self-similar set will again look like the product of self-similar sets, and therefore we can get an explicit formula for the Assouad dimension and the Assouad spectrum when theta is sufficiently large. And this condition in blue here is the condition on theta being sufficiently large that allows this to be the case. But what's more interesting is when theta is smaller than that quantity. And in this case, the correct approximate square to use in the cover is the one which uses the first and third columns in precisely the right ratio, such that the cylinders of height r to the 1 over theta have length precisely capital R, so that they will line up precisely inside the approximate square. So I think what's interesting here is that the squares which look thickest at these scales are not the squares which only use the column with the maximal dimension of the corresponding self-similar set. And then when theta reaches theta min, which in this case is theta 1, then no matter how we choose the approximate squares, the cylinders of height r to the power of 1 over theta will have length much less than capital R. So we have to use the different covering strategy, like the case with Bedford-McMullen carpets and small theta, and we get another phase transition. So we see some interesting behavior relative to the Bedford-McMullen case in that the approximate squares which we work in don't always use the column of maximal dimension, and also that we get multiple phase transitions. What I'd now like to talk about is the intermediate dimensions, which lie between Hausdorff and box dimension, and describe the global scaling behavior of the set in a more nuanced way. And to motivate the definition of the intermediate dimensions, let's recall that the Hausdorff dimension can be defined by covering our set using balls of very different sizes. So it's the infimum of exponents s, such that for all epsilon greater than 0, there exists a finite or countable cover of f, such that the sum of the diameters raised to the s is less than or equal to epsilon. The box dimension can be defined in almost exactly the same way, but with the additional condition that all the sets in the cover have the same size. So this motivated Faulkner, Fraser, and Kempton to introduce the intermediate dimensions, where the sizes of the covering sets are restricted to lie within an interval of the form delta to the power of 1 over theta to delta, where theta is some parameter between 0 and 1. So when theta is 1, you recover the box dimension, and the function that sends theta to the intermediate dimension of any set is going to be an increasing function of theta. It will be continuous when theta is greater than 0, and in nice cases we might hope that it's also continuous at 0. In other words, it approaches the Hausdorff dimension as theta goes to 0. In terms of self-affine carpets, we'll work only with Bedford-McMullen carpets because, as we'll see, it's already very technical in the Bedford-McMullen case. And I'll leave the question of calculating the intermediate dimensions of Lalley-Gatzouras carpets as an interesting open problem. I think that it might be doable using some of the same sort of techniques as for Bedford-McMullen carpets, but it would be much more technical, I think. So Falconer, Fraser, and Kempton proved some bounds for the intermediate dimensions, and in particular proved that they converge to the Hausdorff dimension as theta tends to 0, which can be thought of as a nice regularity property of the set. And Burrell, Falconer, and Fraser used this fact to deduce that if the Hausdorff dimension of a carpet is less than 1, then not only is the Hausdorff dimension of every projection of the carpet, every orthogonal projection of the carpet less than 1, also the upper box dimension of every orthogonal projection is less than 1, even if the box dimension of the original carpet was much larger than 1. And interestingly, this seems to be the only proof of this fact using the intermediate dimensions. So with Istvan Koloshvari, I've calculated a precise formula for the intermediate dimensions of these carpets. And for example, for this carpet on the left, this is what the formula looks like. So we see it's got a much more interesting behavior than has been witnessed for previous examples of natural families of sets. So some qualitative features that we can observe, which also hold for any other carpet with Bedford-McMullen carpet with non-uniform fibers, is that there are phase transitions, so points of non-differentiability at all negative integer powers of this important quantity gamma. Between these phase transitions, the function is real analytic and strictly concave. The function is not just increasing, it's strictly increasing. So as we decrease theta, this really helps to decrease the dimension of the carpet. The right derivative of the carpet, or the left derivative, tends to infinity as theta tends to 0. So when theta is very small, if we decrease theta, that really helps to reduce the dimension by quite a lot. And the overall shape of the graph can vary quite a lot depending on the parameters of the particular carpet, as you can see from these examples. So in my remaining time, I'd like to give an idea of how we prove this in some special cases of theta, starting with the case when theta is greater than or equal to 1 over gamma, and try and give an idea of how tools from probability theory come into play, for example. So this range of theta is nice because cylinders of height delta to the power of 1 over theta will have length that's greater than delta, so they'll extend beyond the approximate square that we're working inside. And it turns out that we can use a cover which only uses the 2 extreme scales for this range of theta. This is very much not the case for smaller theta, but for this range of theta, this is the case. So if we let capital K be such that n to the minus k is approximately delta, then given an approximate square with a certain symbolic representation, we'll want to keep it at size delta if and only if the s cost of covering it at size delta, in other words, the diameter delta raised to the power of s, is less than or equal to the s cost of subdividing it. So that s cost of subdividing it is delta to the power of s over theta times the number of smaller approximate squares which lie inside it. And if we compare symbolic representations, this number of smaller approximate squares inside it will be given by m to the power of gamma k over theta minus gamma k times by the number of cylinder sets of height delta to the power of 1 over theta inside this approximate square. And that number of cylinder sets will be given by this product of the number of maps in each of the columns in its symbolic representation. And if we take logs and rearrange this, this says that this average of the logs of these number of maps in the columns of the symbolic representation will exceed this quantity here in terms of s, where s is still an unknown parameter at this stage. And we call this quantity T1 of S. So to work out how many squares we need to keep at scale delta according to this covering strategy, we use tools from probability theory. So let x1, x2 be an IID sequence of random variables uniformly distributed on log n1 up to log nn. And then the number of scales which we keep at scale delta, the number of squares which we keep at scale delta is the total number of strings of this length, so of columns, so strings of columns of this length, so that's capital M to the power of k over theta minus k, times by the probability that the average of these random variables up to this time will be greater than or equal to this quantity T1. And this probability that this average is greater than or equal to this is going to be given by e to the power of minus k over theta minus k times this rate function I of T1 by Cramer's theorem. So we're now in the realm of large deviation theory. And this rate function is given by the Legendre transform with this formula here. And in simple cases, this can be calculated explicitly, but in more complicated cases, we can still calculate this numerically, which is how we managed to draw the plots of the intermediate dimensions before. To show that the calculation on the previous page gives the correct S cost of this cover, we need to use the method of types. And the key observation here is that the cost of subdividing a particular approximate square to the smaller scale doesn't depend on the precise positions at which the columns in its symbolic representation appear. It only depends on the frequency with which each column appears. So we therefore group all the approximate squares in our carpet into type classes depending on this digit frequency of the columns. And the total number of approximate squares grows exponentially with k or delta, but it's easy to see that the number of type classes grows only polynomially. So this means that the dimension of the whole carpet will be carried, as it were, by only one critical type class, depending on S. And if we again use Cramer's theorem to calculate the cost of covering each type class, we will see that the critical type class will have the average on the previous page equal to precisely T1 of S. In other words, it will have the same S cost whether or not we subdivide. Now, in order to show that there's no other covering strategy using more scales that will give us a smaller S cost, we put an appropriate measure on this critical type class of the carpet and then apply an analog of the mass distribution principle for the intermediate dimensions to give a lower bound on this S cost. And now to calculate the intermediate dimensions from this, we need to determine the value of S for which this S cost neither blows up exponentially nor decays exponentially as the scale delta goes to 0. And that value of S, it turns out, will solve this equation. So this is the most explicit form that we can give the intermediate dimensions in for this range of theta. Another set of values of theta which are easier to deal with than the general case are when theta is given by gamma to the power of some negative integer. And the reason why this is a nice case to consider is if we take an approximate square of size delta, then a cylinder whose height is delta to the power of gamma will have length almost exactly delta, so it will line up nicely inside it. And if we take an approximate delta to the power of gamma square, then a cylinder whose height is delta to the power of gamma squared will line up precisely inside that square. And in this case, the covering strategy, which gives us the intermediate dimensions, will be to keep an approximate delta square at size delta if and only if the average of these logs of the number of maps in the columns exceeds the same quantity T1 of S as before. But if this is not the case and we have to subdivide our square, then we have to look at each of the smaller squares individually and keep it at the scale delta to the power of gamma if and only if the average of these logs corresponding to its symbolic representation is greater than or equal to some new quantity T2 of S. And repeating this process gives us a cover using the scales delta, delta to the gamma, up to delta to the power of gamma to the L-1, which is delta to the power of 1 over theta, in terms of these thresholds, T1, T2, etc. And now if we again use Kramer's theorem to calculate the S cost and optimize these thresholds Ti so that the S cost of each of these parts of the cover is equal, right? This is the optimal strategy. Then it turns out that we should choose Ti of S to be given by this function capital Ts of the previous threshold, where capital Ts of some number T is T1 of S plus gamma times I of T. And if we again choose the value of S for which this S cost neither blows up nor decays exponentially, then this will solve this equation here, which will be the formula for the intermediate dimensions in this case. Finally, I'll conclude by mentioning that in the most general case of theta, things are a lot more complicated. So this is where theta lies between two integer powers of gamma. And here we have to use not just the scales delta, delta to the gamma up to delta to the power of gamma to the L-1, but also we have to use the smaller scale, delta to the 1 over theta, etc., up to delta to the power of 1 over gamma to the L-1 theta. So this is intuitively why we get these phase transitions at negative integer powers of gamma. It's because the number of scales that we need to use in the optimal cover will jump up by 2 every time we pass such a power of gamma. And here we don't have fixed thresholds like Ti of S for which we need to see whether the average of the logs exceeds it or is less than it. We have to look at how different parts of the symbolic representation of the squares compare with other parts of the symbolic representation of the same squares. So it's a much more complicated strategy in this case, which I don't have time to discuss too much more, unfortunately. But it turns out that the value of S, which gives the intermediate dimension in this case, is given by this formula, which is again in terms of the rate function I and these quantities T sub L of S, which we defined a couple of slides ago. Okay, that's all that I've got to say, so thank you for listening.